In this section, we're going to explore another application of the derivative, which is optimization. And if you think about it, so far this chapter has been all about analyzing the behavior of a given function's graph. And the way we did that is by studying its first and second derivative. That's really how sections 4.1, 4.2, and 4.3 kind of funneled into section 4.4, where we put everything together to do curve sketching. But now we're going to apply a similar strategy in the case where our given function at hand just happens to supply the value of a real-life quantity that we wish to either minimize or maximize. And we're going to start with an example of an optimization problem. So if we read this carefully, we've got a farmer, and the farmer has some fencing available. So it's got a specific amount of fencing, 2,400 feet of fencing, and the goal is to enclose a rectangular field which is adjacent to a river. Now the question is, well, what is the largest area that you can possibly manage to create by doing this? What's the, in other words, if you actually have this fence that encloses a rectangular field, what's the maximum area of this rectangular field in the sense that it's a rectangle? You can measure its area. So what is the largest area possible? But also what you want to know is what would the dimensions of the fencing have to be in order to enclose it? And by it, we mean the maximum area possible, right? So there's two questions here. What's the largest area you can possibly enclose? And then the other question is, well, how are you going to actually accomplish that? What dimensions are you going to have to make the fence in order to make that a reality? Okay, so it helps to start with a picture. So that's what we'll draw now. We'll start by just kind of drawing a diagram of what this is going to look like. And there's an important part of this fence. Yeah, it's a rectangular fence, a fence that goes around a rectangular field, so you could call that a rectangular fence, but it's adjacent to a river, and that's really important. And you'll see why in a moment. When we draw the river, which I'm just going to sketch it like this, I'll just write the word river so we know what I'm trying to draw there. That's the river, let's say. Now if I draw a fence around a rectangular field that's adjacent to this river, you'll notice that I really only had to draw 3 line segments, right? So one of the sides of this rectangle or one of the borders of this rectangle is already accomplished by the fact that there's a river there. The idea is whatever livestock you're kind of containing in that rectangular field, they're not going to go into the river, so you really only need to fence off their travel in 3 other directions. If they have whatever animal here, it can't go east, can't go north, and it can't go west. But the river is going to prevent it from going south, so we don't need to put fencing along that side. Okay, well, let's start labeling some things so we actually have something to work with. So you might, one of the things that we're going to be interested in is the length of this fence here, which is also going to be the same as whatever this length is here. So let's call this x, right? And we can call this other side length of the rectangle y, and then we could just specify that those are going to be 2 measures of distance, and the units we're going to use for both of them, we might as well measure them in feet, since the units that we're given here, the fencing that we have is 2,400 feet, so we might as well mention that x is going to be a distance measured in feet. So how about we just say this, distance in feet, and then y can be the same thing, distance in feet. All right, and it's worth mentioning at this point that there's a very particular domain of consideration that we're going to restrict ourselves to in the case of this diagram, right? This value of x, is it ever going to be negative? No, you're not going to have this side length be -1. You're not going to have a side length of -1 feet. And you're also not going to have a side length of 0 feet, because if x was 0 here, you'd really have no rectangle. Right, the fence would be a complete waste. You'd have a fence just going along here, right along the river, and you'd have no fence at all. And similarly, for the same reason, y can't be negative, and it also can't be 0. So it's worth specifying that early on in the process, just to avoid any potential contradictions down the road. So we need both x and y to be positive. So I refer to that as the domain of consideration. We're only considering potential solutions to this problem that satisfy these 2 inequalities. So we need x and y both to be positive, so we really truly do have a rectangular field. Some other things that we can talk about and that are going to be irrelevant, well, first of all, area. We should talk about the area, because that's the central theme of this question, is what is the largest area possible? Well, so why don't we write that down? Let's write down A for the area. And well, we can also write down a formula for it, because the area of this rectangular field is going to be the product of the 2 dimensions. So A is going to be equal to x times y, and I'll just mention that that's area. And then the other thing that is going to come into play is the perimeter of this fence. Now, the word perimeter does not appear in the statement of the problem anywhere. However, it implicitly is mentioned here in the fact that the farmer has 2,400 feet of fencing. So really, if you add up this distance to this distance to this distance, that can't be any greater than 2,400 feet. Now, and you can be a little more specific than that, and you might as well just say that it had better be equal to 2,400 feet, because if you're going to try to, if you have fence left over, there's no way that you've made the biggest rectangular field you possibly could, right? So the optimal solution is going to use up all of the 2,400 feet of fencing. But really the quantity we're talking about there is the perimeter of the fencing. So let's actually mention that. The perimeter of this rectangle, we can write it as 2x. And what's the formula for perimeter of a rectangle? Normally you'd have 2 times x, because you'd have this side and this side, plus 2 times y, because you get the top side and the bottom side. However, remember there's no fencing down here along the river. The river is really acting as that fourth wall. So we're actually going to go 2x plus y, as opposed to 2x plus 2y. And so that's going to be the perimeter. Okay, so most of this is just kind of setting up some preliminary material so that we can actually phrase this optimization problem mathematically. Now we're ready to do that. So optimization problems typically have two main components, right? The first thing is called an objective function. It's the thing that you're trying to optimize. Now, and that can mean one of two things. You're either trying to maximize the objective function, or maybe you're trying to minimize the objective function. But in this case, we're trying to maximize it because we want to find the largest area we possibly can to be enclosed by this fence. So let's translate this problem as the following. So maximize. We want to maximize the area, which is given by A equals x times y. And the other component of an optimization problem is the constraint. And quite often there's multiple constraints. Like for example, we have a couple of constraints right here, right? We need x and y both to be positive. So whatever the optimal solution is, it's not going to be one where x or y is negative. But it's also not going to be, we're not going to obtain the optimal solution by taking x to be 10,000 feet and y to be 10,000 feet. That would get us a very large rectangular fence, or a very large rectangular field, but it would not satisfy this. This is our real constraint here, this limitation that we only have 2,400 feet of fencing to work with. So that's really the other constraint to consider. So we'll say subject to well, the perimeter has got to be equal to 2,400. Okay, so that is an optimization problem. We've now completely translated this word problem into an optimization problem. You've got an objective function, the thing you're trying to maximize or minimize, and you've also got the constraint. Now, like I said, technically these are constraints as well. If you want to actually formally include them in a list here, you can. And quite often, optimization problems, you'll have a list of constraints. But I would say this is our main restriction. This is our main constraint that's going to lead us to the solution. And these are just kind of assumptions that we make in the background, just so that the problem even makes sense at all. Okay, so let's now look at how to solve this. So, well, how are we going to maximize this objective function? Well, do we know how to maximize functions right now? We do know how to look for maximums, right? We could find critical numbers, do the first derivative table, look for places where the function changes from increasing to decreasing. That's typically how we find the location of local maximums. Or you might consider a closed interval method. But all of those, or everything, all the techniques we've talked about so far, they really apply to functions of a single variable. But this is a function of two variables. So it may seem, at least at first glance, like we're going to have to develop a new strategy to deal with this. But it turns out that this constraint here is going to actually turn out to actually help us. Because this constraint is actually going to, if you carefully look at this constraint, it actually turns out that this is actually a function of one variable. It isn't written out in front of us just yet. So let's first consider this. If I have P is equal to 2,400, the perimeter is equal to 2,400, and the perimeter is also, well, by definition, based on our diagram, the perimeter is 2x plus y. Well, that tells you that 2x plus y is equal to 2,400. So really what that does is give you a relationship that x and y have to always satisfy. And in particular, it allows you to actually isolate y in terms of x, and you're going to get y is equal to 2400 minus 2x. So if y is always equal to 2400 minus 2x, then y is completely dependent on y. Or pardon me, y is completely dependent on x. So a is also completely dependent on x because it's dependent on x along with another variable who is also dependent on x. So we can rewrite a as, well, x times y. That's just what a already is, the area is already written as. But we can write it as x times 2400 minus 2x. Right? And now the area is a function of x. And if I go one step further, I can even expand this and write it as a polynomial. Now I have 2400x minus 2x squared. Okay, so that is the objective function written with a single variable. Right? It's a function of a single variable. So now we can use the techniques that we've already developed in Chapter 4 so far. So how are we going to find local minimums and maximums? In our case, we're looking for a local maximum. Let's take the derivative and look for a critical number. That's a good place to start. Right, so let's take a prime, differentiate this polynomial, and you're going to get 2400 minus 4x. And actually, you can factor out a 4. And you can write this as 4 times 600 minus x. And actually, that's going to give us our critical number right away, because a prime is equal to 0 exactly when x is equal to 600, because that'll make this factor equal to 0. Okay, so that is our critical number. Now, are there going to be any other critical numbers? Do we have to look for type 2 critical numbers? Our a prime is equal to 4 times, well, even just look here, a prime is equal to 2400 minus 4x. That's a linear function, right? It's a specific type of a polynomial which is defined everywhere. So you're not going to have any type 2 critical numbers. So this is the only critical number. So when we go to do our first derivative table, we only have one critical number to worry about. So let's set that up now. So we can set up our first derivative table. Let's do one row for a prime and one row for a. Right, and we've got our one critical number of 600. Right, so this is nothing new. This is just what we've always been doing in Chapter 4, or I guess it's more specifically in Section 4.2 and 4.3 and 4.4. Right, this is nothing new though. The only difference is we, instead of just some function f that has no connection with reality, we have a concrete function of a single variable that happens to represent a real-life quantity, which is the area of this fence, or area of this rectangular field that we're trying to enclose. So really we're not doing anything different, because now we're going to pick some sample points. How about something slightly smaller than 600? But there's lots of options, but I'm going to choose 599 and 601 as my sample points. And if you plug those into a prime, 599 plugged into a prime, look up here. If you plug in 599 for x, you're going to get 600 minus 599. This is going to just equal 1. So you've got 4 times 1, which is going to be positive 1. In particular, it's going to be positive, right? So your function a is actually increasing for values of x that are less than 600. So the closer the value of x is to 600 on this side, the larger the area of the fence is going to be. So now the question remains, well, what happens if we go past 600? What if I move the value of x even further to the right? Is it going to continue to increase, or is 600 going to be where it stops increasing? That's the question at hand. And if we can answer that question, we've solved the problem. Okay, so what happens if you plug 601 in? Well, if you plug in 601 for x, then a prime is going to be 4 times 600 minus 601. And 600 minus 601 is going to be negative 1. So you really have 4 times negative 1, which is negative 4, or negative. So the function a is decreasing. So that confirms what we've been hoping for, is that this is actually going to be where the area is maximized. That's the value of x that you want if you want to maximize the area, because the area function a has a local maximum here. Okay, and just a comment, there's lots of options here for for the sample point that's to the left of 600. But I can't get too carried away, right? Because remember, we did have another constraint on x, which was that x had to be positive. So a lot of times this doesn't come up, but you do want to be aware of it. Technically, there's a left bound here at 0. I cannot go any further to the left of 0. So if I had used negative 300 as a sample point here, technically that's less than 600, but that would not make sense for this problem. You have to stay within the range that you care about. And similarly, when I looked for my critical numbers, right, we only found one, x equals 600. Well, sometimes you get more than one critical number, right? And sometimes some of them are positive and some of them are negative. But in this case, since our problem insists that this quantity x be positive, we would have thrown away any critical numbers that we found at this stage that were negative. Right? So that's just something to keep in mind in the future. But now we've got ourselves a local maximum, or at least we got the location of a local maximum, right? Let's use that value of 600 to get all the rest of the information, right? Because that's only part of the story. If someone asked you, how do I build this fence so that the area is maximized, you're not just going to just tell them what x is. You're going to tell them what x is, what y is, and you're going to tell them what the area of the fence is. And in fact, that's what the question asked for, right? We're asked for what's the largest area possible, and we're also asked for the dimensions of the fence in order to enclose the largest area possible. So let's answer all those questions. So when x is equal to 600, let's actually mention our finding here. So A has a local maximum when x is equal to 600. That's the most important part of that comes from our work over here. So, well, what is y when x is equal to 600? So when x is equal to 600, well, y is going to be 2400 minus 2 times 600, right? That 600 is going to get plugged in here, and that's going to tell us what y is. So we'll have 2400 minus 2 times 600, and I could just squeeze it in over here, which is going to give you 1200. Because 2 times 600 is 1200, subtract that from 2400, and you're going to get 1200. So that tells you what y is. So let's answer the second part of the question first. The dimensions which maximize the area are what? Well, 600 feet by 1200 feet. Let's just put that, 600 feet by 1200 feet. Okay, so don't forget to put your units back into the problem, right? At this stage, x and y measured the distances in this diagram, but they were both measured in feet. And then the second part of the question was, and it was actually asked as the first part of the question, but what is the largest area possible? Well, how do you get that? Just multiply these two numbers and you'll get the largest area possible, right? We've already done all the work. The rest is just kind of a formality. But if you multiply 600 and 1200, what you're going to get is 720,000. So let's finish that off. So the maximum area possible is 720,000 square feet. So you'd say 720,000 feet squared, just like that. Okay, and that's how we can solve an optimization problem. Okay, so let's finish that off. And there's actually another technique that we can use that will sometimes save you some work. And that's actually what I'm going to talk about next before we look at the next example.